Also, check out the second channel, Papa Flammy 2, for way more magnificent maths content over there. I'm covering a lot of basics there, but with a touch of rigorousness and higher mathematics, so it's pretty cool. Check it out if you're interested. A huge thanks to my Patreon supporters for making this episode possible. Good morning, fellow mathematicians! Welcome back to another video. We are going to do engineering clock today, only available for a limited amount of time, blah blah blah, link at top of the description, and so on. Get them limited. Once they are gone, they are gone. We are going to talk about something really fundamental today. We are going to talk about the derivative with respect to xt, whatever the frick you want, of the inverse hyperbolic sine of some function f with respect to x. Prerequisite knowledge for a very interesting video coming on Friday or something, or Wednesday, I don't know yet, but we need this here. And this is some really nice application of implicit differentiation we're going to do today. So if you don't know what that is, then yeah, well, here's your basic introduction to implicit differentiation. At first, I would just like to note that the sinh, the inverse sinh of f of x, is just some function y with respect to x. So what we are actually looking for is some ddx of a differentiable function y of x. And this is where we are going to start off. We are going to say that the inverse sinh of f of x is nothing but y. Okay, so we are going to let area sinh of f be equal to y. And now we are going to assume that our sinh is invertible, meaning we have a bijection. This only works on certain intervals. We are going to just assume that we can use the inverse sinh on both sides now, meaning overall f, so the sinh of the inverse sinh is just the identity function, and spitting out the function in here, just the argument, is thus nothing but the hyperbolic sine of our boy y. And now we are going to differentiate both sides with respect to x here. The reason for that is simply because y of x is a function with respect to x. When we differentiate sinh with respect to x, then we have to use the chain rule, meaning we have to also take the inner derivative, which is going to be exactly y prime right here. Okay, I hope you can see where this comes from. So we are going to differentiate both sides with respect to x. So del x of f is thus del x of the sinh of y. Now we are going to take the outer derivative and we are going to multiply it by the inner derivative. Okay, this is just the chain rule here. Also, the derivative of f with respect to x is just something that's there. If f is differentiable, then we can just take the differential on both sides, all right? So we're going to concentrate on the right-hand side for now. This is going to give us, okay, on the one hand, the derivative of sinh is nothing but the cos. So sinh is defined in its Euler form as e to the x minus e to the negative x over 2. If you differentiate that, you are going to get e to the x plus e to the negative x over 2, which is exactly the cos. So for the outer derivative, we are going to have cos of y times, well, the derivative of y, just using the chain rule here, y prime. I'm going to denote it like this. And now we can exactly solve for y prime here. Okay, this is what we are looking for. Y prime is the thing in question we are looking for. We're going to divide both sides by cos of y under the condition that it's not equal to 0, leaving us with y prime being nothing but, well, the differential of f with respect to x divided by the cos of y of x. Now here's the thing, if we just let it stand like this, we have a differential equation because our differential is with respect to itself yet again, y. This is not something that we want, but the cool thing is we can actually substitute our value for y into here. Then we are going to get the cos of the area sinh of f. Okay, so what we have here, so this thing is equal to this thing. We are going to have 1 over the cos of the inverse sinh of f times the derivative of f with respect to x. Now we just need to find out what cos of the inverse sinh actually is. It's pretty easy to derive because there's an analogous formulation for the fundamental theorem of trigonometry just for hyperbolic functions. You can easily derive this using the Euler forms we have talked about before. I haven't derived it yet on this channel, but it's really easy. Or you can just use imaginary arguments on the fundamental theorem of trigonometry, and you're going to get the same step out. What I'm talking about is that 1 is nothing but the cos squared of some argument eta here whatsoever, really doesn't matter, minus the sinh squared. And now we are going to solve for the cos, only taking into consideration the principal branch here. It really depends on your argument, etc. pp. What we are going to get out as a sine, but by solving for the cos, we are going to get the positive square root of 1 plus sinh of the argument we have in the cos. Let's say this is cos of x, sinh of x, and the whole thing squared. Now just imagine that we are going to plug the inverse sinh into our cos here. This is going to give us the square root of 1 plus sinh of the inverse hyperbolic sine of f in our case. If we apply the function to the inverse function or the inverse function to the function, I should rather say, it really doesn't matter, it's a bijection, so both works, then we are just going to end up with the identity function or the argument in here in itself. Meaning, overall, we are going to end up with 1 over the square root of 1 plus, and our sinh of inverse sinh is going to be just the argument f and the whole thing squared. So f squared times the derivative of f with respect to x. And then we are done. So now we know what the derivative of the inverse hyperbolic sine is. The area hyperbolic sine, this is what they are called, not the arcus hyperbolic sine. For the hyperbolic function is the area hyperbolic things. Okay, just in case you didn't know, at least it is in German, so it is something that not many people know, but this is it. Thank you guys for watching, just a little chill video here on this Monday. Okay, I'm going to go to the outside now and we're going to do some grocery shopping now. That's going to be freaking great. Other than that, engineering vlog. Also, check out the second channel, Papa Flammy 2, for way more magnificent maths content over there. I'm covering a lot of basics there, but with a touch of rigorousness and higher mathematics, so it's pretty cool. Check it out if you're interested. And other than that, I wish you guys a wonderful day. Ciao!